Video 5. Peak sun hours and insolation. Peak sun. Another measurement installers use when designing a PV system is peak sun. Peak sun is the maximum solar irradiance available at most locations on the Earth's surface on a clear day, 1000 watts per meter square. 1 hour of peak sun is known as peak sun hour. Peak sun hours is a measure of solar irradiation, watts per meter square per day. Peak sun hours are calculated at a given location by determining the total irradiation, watt-hours per square meter, received during daylight hours and dividing that number by 1000 watts per meter square. On a summer day, for instance, the solar irradiance may average 600 watts over 12 hours. So as a result, the total solar irradiation is 7200 watt hours, and peak sun hours is 7200 watt hours divided by 1000, that is 7.2 hours of peak sun. Even though the peak sun hours per day is 7.2, solar irradiance may only reach 1000 watts per meter square for 2 hours. Sun and the Earth. Understanding the relationships. Now that you understand irradiation, peak sun and peak sun hours, let's examine the geometric relationships between the Earth and the Sun. Day length and altitude angle. The Earth's tilt and orbit around the Sun. As you learned in grade school, the Earth orbits around the Sun, completing its path every 365 days. The Earth's axis is tilted 23 degrees. The Earth maintains this angle throughout the year as it orbits around the Sun. The angle remains fixed, almost as if the Earth were attached to a wire anchored to a fixed point in outer space. Because the Earth's tilt remains constant, the northern hemisphere is tilted away from the Sun during the winter. As a result, the Sun's rays enter and pass through Earth's atmosphere at a very low angle. Sunlight penetrating at a low angle passes through more atmosphere and is therefore absorbed or scattered by more dust and water vapor. This in turn reduces irradiance, which reduces the output of a solar array. Solar gain. Solar gain is also reduced in the winter because the days are shorter, that is, there are fewer hours of daylight during the winter months. Day length is determined by the angle of the Earth in relation to the Sun. During the winter, in the northern hemisphere, most of the Sun's rays fall on the southern hemisphere. All three factors, lower energy density, increased absorption, and shorter days, reduce the amount of solar energy available to a PV system in the winter. In the summer, in the northern hemisphere, the Earth is tilted towards the Sun. This results in several key changes. One of them is that the Sun is positioned higher in the sky. As a result, sunlight streaming onto the northern hemisphere passes through less atmosphere, which reduces absorption and scattering. This in turn increases solar irradiance, which increases the output of a PV array. Because a surface of the Earth is perpendicular to the Sun's rays, it absorbs more solar energy than that's tilted away from it. The Earth's surface intercepts more energy during the summer as well. The high-angled sun delivers much more energy per square meter of the surface area than in the winter. Moreover, days are also longer in the summer. All these factors increase the output of an array. And here ends video 5, peak sun hours and insolation.